Okay, hi everyone. So now we move to a new chapter, which is the last chapter of your course, Engineering Maths 2, SSCE 1993. Okay, so what is in the chapter 5? As in chapter 4, I already introduced you some of the important thing in the vector calculus, where you have done differentiating some of the vector function and sketching of the vector function and so on. So now we move to or we extend the important thing in the vector calculus, where it is about the integral of the vector function. Okay, so what is the thing that we want to focus in this chapter? So we have two important things here, where we have we call that the first one is line integral. We have a line integral, and the second one we have a surface integral. Okay, so for the line integral, in this case, what we have to look is there is a word integral, so you have to integrate. So in this case, you have to deal with the single order integration. Okay, and then for surface integral, you have to deal with the double integral. Okay, where this one is the extension from your chapter 3, but the difference here is you will also need to consider the function, but in a vector form. But in chapter 3, we only deal with the function where it is just a scalar form. Okay, so about the surface integral here, the way you want to integrate the kind of function where it is whether a scalar field or vector field is the same as in chapter 3. Okay, so the application that we will focus in this chapter is we will learn something about the conservative vector field, and then part of that we will look at the one theorem which is called as the Green's theorem. Okay, these two subsections is they are under the line integral, but you have another theorem where it is namely as a Gauss theorem and a Stokes theorem, where these two theorems are under the surface integral. So this is the thing that we will focus in this in the last chapter, which is chapter 5. Okay, so next we will look at what is the line integral.
So in general, the line integral in general is denoted by you have a single integration and you have the function as the integrand with respect to ds. In this case, ds is the arc length. Okay, so what we can say here, the line integral is actually we integrate over a curve C. Okay, over a curve C. So your integral here, if 2D, for 2D system, you have, your integral here can be just in terms of x or y, or the x and y. But in space, if the curve in space, you have another variable which is z. So this is a 2D system, but in 3D system, we have the f, x, y, z with respect to the arc length over the curve C. Okay, so the inside the line integral, this one in general, so we have the scalar field, and also we can have the vector field. So you have you can have two kind of function, scalar field or vector field. So I will teach you how can we evaluate the line integral for this specific function, the scalar and the vector field. Okay, so what is normally the application or the problem involved with the line integral? So It can be the fluid flow, forces, electricity, and magnetism. And you can also evaluate the area under the curve, or you can also evaluate the mass of the very thin wire, which that wire or rope is represented by the curve. So we can, meaning that we can also use the line integral to evaluate the area under the curve and also the mass of the very thin wire or rope. Okay, so that is the application of line integral. Okay, so what is the thing that you have to have, or what you have to need in order for you to compute the line integral? Okay, so because of the formula that you have, you look at here, so there is the ds. Okay, because normally the information provided to us, there is no direct information regarding the arc length. So you have to have the formula to convert from the information provided into the ds. So when we go back or we recall some information or the lesson that you have learned in method 1, I suppose, there is a topic on the arc length, if I'm not mistaken. So you can compute the arc length using this formula. Okay, so because now we have we want to get the ds, but the information provided for the curve normally in terms of the parametric equation, or we can say it is a vector. Okay, so the curve is given by a vector function in terms of t. So now you have to be able to convert the information that you have into the ds. So the formula that you have to have is you have, how can you have the ds here? So actually ds is just like the arc length is the magnitude of the, because you have the ds, meaning that something related to differentiation. So ds is a magnitude, I mean a scalar function, something scalar, but the information provided to you, it is a vector. So then whatever vector that you have to find its magnitude, so that from vector you can have a scalar, right? Okay, so how can we have this particular formula? So actually we can use the idea that so we have the ds. Maybe I should, okay, ds over dt is dr over dt, because the left side is for scalar form, then the right side it is a vector r, and now when you differentiate, still a vector, but you want to obtain the scalar value of this, so you have to find the magnitude. Okay, so then because we are only interested on finding the ds, so ds is dr over dt, magnitude, multiplied by dt. So this one is actually r prime t, and you have to find the magnitude dt. So meaning that using this one, because we have the information in terms of t, right? So instead of we use the ds directly, so you have to find the derivatives of the vector function, and then after that find its magnitude, and you can have dt at the back. So now this is something that the common information that we have. Okay, so what is the r prime? Okay, so we know that rt is given by, this is a vector given by x in terms of t, y in terms of t. This is if it is in two-dimensional system, only x and y. So when you differentiate, So r prime t, and you have dx in terms of t, and you have dy in terms of t. Sorry, it should be dx dt, dy dt. Okay, and because we want to get its magnitude, so we just have x prime t square plus y prime in terms of t squared, and there is a square root outside. So that's why we have this one. Okay, so this one is for 2D system where there is only x and y. But if you have 3D system, you have to add the z here. Okay, you have to add the z in terms of t, and this one you have dz over dt, and you have, for finding the magnitude, you have the z prime in terms of t square. So that is for 3 space. Okay, if your information, your curve is in space in 3D system, but if your curve on 2D system, so you just have x and y. Okay, so you need to have this in order for you to convert from the single integration respect to arc length to the single integration respect to t, because as I mentioned before, the information provided to us is normally in terms of t. So you have to have the formula to convert from arc length to the t. Okay. Since I mentioned just now, line integral, there are two kind of function when you want to deal with the line integral. So whether it is a scalar field or vector field. So which means that the integrand, the information of the integrand that you have is a scalar field or vector field. So now we start with the finding the line integral for scalar field. Okay, just now I mentioned that what is the physical meaning of the line integral. Okay, so the physical meaning of line integral, especially for the scalar field, is actually we want to get you are evaluating a mass of the very thin wire or very thin rope, or another physical idea regarding the line integral for scalar field. If you look at this in the notes, it says that consider the problem of how much mass a worm munches through when digging along the line given. Okay, suppose that the soil, so imagine there is a worm munching the soil, so the density function of the soil is delta, which is the integrand. So this one is the density function. So this one is actually line integral. So from this line integral, so we can determine the mass of the worm munching through the curve given. So the curve is a line on 3D system or on 2D system, depends on whatever integrand that you have. If there is only x and y, so we know that the function is only about the x and y, about 2D. But if there is x, y, and z, and it is a 3D. Okay, so now how can you evaluate this one? So firstly, you have to convert ds to dt by using the formula of this one is actually, if you relate this with the something kinematic, right? So r prime is the velocity, and the magnitude of r prime is the speed, right? So this one we consider, we can also call this as a speed. Okay, so now we managed to convert from ds to dt. So what is the r prime magnitude? So as I mentioned before, so now we can say that line integral of a scalar field, we are actually computing the mass of what? For this particular case, so we're assuming that the mass of the worm munching through the curve given by the vector function rt. Or maybe instead of we have worm, we have a very thin rope or very thin wire. So you can evaluate the mass of that particular wire or rope. along the curve given. Okay. So we call this as this is called as a line integral of the density function f along the curve C. It is also called a line integral with respect to arc length. So that is a line integral. So this is specifically for a line integral of a scalar field. Okay, instead of we assuming that we compute the mass of the rope or the wire or the worm munching along the curve C, we can also explain the line integral for this particular scalar function. Okay, this one. So we can also elaborate this to be the area under the curve. By using the same formula, we can interpret this to be the area under the curve. So you can see this one, let's say this is just like a washing line. Okay, washing line. Tempat you sidai baju kan, ni line ni. So you sidai blanket. So you have a blanket. So now you can evaluate the area of that blanket under the washing line. So using the similar formula, which is a line integral. So this is how we can interpret. So it depends on the problem that we have. So the formal definition of the line integral for scalar function f. So this one. So this is the line integral for scalar function f. Okay, when your C is on 2D system. As I mentioned before, we can interpret this to be the area under the or below the curve. You have a curve given by the red line, this one, right? So you can evaluate the curve, sorry, the area under the curve using the line integral. So this one, if your curve C is smooth, okay, you can see it is smooth, right? But sometimes you can have something not so smooth, but yeah, still this one. So actually we just say that the line integral that we have here, we are computing the area under the curve, or if you're talking about the mass, so we are computing the mass of the line. You can see this is the line, right? And we can evaluate the mass of this line, the mass of this red line. So now we want to look at how can we evaluate the line integral for, so we start with the scalar function. Okay, so normally your curve, because if you look at your line integral here, so in general we want to compute the integration of the function f in terms of x and y along the curve C. So you must have the information about the curve. So normally the curve is given by in a vector function where you can have the parametric equation. So from the vector function that you can have, you can evaluate the speed. So this one is actually the formula of speed, which means that you have to differentiate the x component and the y component and then evaluate the magnitude. Okay, so for 3 space, when your vector function there is x, y and z, and you have to, from the vector function provided about the curve, you have to take out the parametric equation for x, for y component and for z component, and you have to do the same procedure as the first. I mean, from this is 2D system, this is 3D system, so you have to evaluate the speed as well, but you have to take note you have the z now. So that is the formula of the speed. Okay. So this is in general. Okay, so now how can we implement that? So we have to look at the example here. So I know that the solution is provided, but just ignore that for a while. So we want to focus on finding or evaluating the line integral when the integrand is a scalar field. Okay. So you can see here, in order for you to evaluate the line integral, you must have the integrand, okay, and you must have the information about the curve. So now you have two questions here. So using the same integrand, so our curve is different, because why I'm saying different, because we have a different vector function. So I'm assuming we have a different curve. Okay, so your curve is given by in vector form and t from 0 to 1. Okay, so to answer this, okay, so we have example 1, 2.1 supposed to be 2.1. So the line integral, we have 1 plus xy square ds over the curve C. So your curve C is given by the vector function of t and 2t. And your t is between 0 to 1. Okay. If you look at the technique in general, after you compute the speed here, so everything should be in terms of t. So because of you integrate all the integrand here respect to t, and you have to have the limit of t. Okay, so if it is given, so then you are very lucky, you don't need to find it. But if it is not given, then you have to find yourself. So in this case, these are given, right? So t from 0 to 1. Okay, so so you have to find the in this case x is t and the parametric equation of y is 2t. Okay, so because of, you can see that the formula of the speed, you have to differentiate x respect to t, y respect to t. So you have the x prime will give you 1, y prime will give you 2. Okay, and then you have to find the, as we know that the ds is the magnitude of r prime dt. So you have to find the square root of, so what is r prime? So r prime, or we can just have the directly differentiate. So r prime in terms of t, then you will get 1, 2, right? And then we can evaluate its magnitude. Which means that the square root of 1 plus 4, so you will get square root 5. So in this case, you can get the speed is given by square root 5 dt. So from here, we can, instead of we deal with ds, so we manage to convert ds in terms of t. So we have 1 plus xy squared, and your ds is square root 5 dt. And what is the limit of t? So it is provided. So t is from 0 to 1. So can we directly integrate now? Can we? So look at your general step. So you must be able to change everything in terms of t, meaning that you still cannot directly integrate respect to t, because your integrand here, there is still x and y. You have to convert, you have to substitute, or you have to convert your integrand here into t. Okay, so now you focus on the integration, the integrand. So your integrand, your original integrand, is 1 plus xy squared. So you have to convert into t, so you have to plug in x equal to t and y equal to t. So 1 plus x, so x is t and y is 2t squared. So 1 plus t 40 square will give you 1 plus 40 cube. So now your line integral become 1 plus 40 cube square root 5 dt, t from 0 to 1. So now you can see that your line integral with respect to arc length now converted into dt. So for this you have a regular single integration where you can just integrate as usual. Okay, so this is the line integral that we have. So first you are given something in terms of arc length, then you have to convert ds in terms of in terms of dt. Then you just plug in your new ds into your line integral. So now everything is in terms of t. After this, so you can integrate as usual. So no more line integral. It's just a common line, a common single integration. So you because this one square root 5, so you can take it out. And now we want to integrate 1 respect to t, so you have t plus t4. And then replace t from 0 to 1, and then you will get 2. So your answer is 2 square root 5. Okay, so it's not so complicated, right? So this is the procedure for you to evaluate the line integral for scalar field. Because for the vector field, we have a different step. For the first, we have a different step. But after some steps, it reduces to a common or regular single integration. Okay, so now look at the second one. So look at the second one. Okay, for the second one, we have the same line, the same integrand. So xy squared ds. Now the difference c, where your c is given by the vector function. You have 1 minus t and 2 minus 2t. That's it. Okay, and also the limit of t is provided, 0 to 1. Okay, so now you have to find the ds in terms of dt. So to get that, now look at your r. Your r is 1 minus t, 2 minus 2t. So you have to find the derivatives. So you will get minus 1 and minus 2 and find its magnitude. So you have square root 5. So then we can get ds is r prime, magnitude of r prime, d. So what is the magnitude of r prime? We already get square root 5. So it's not necessarily we will get only a value. It also can be in terms of t. That's why here I put the r prime in terms of t. So there is a possibility your speed can be in terms of t. Okay, but we do hope that all the time you have this constant so that our integration will become easier. But it depends on the integrand that you have. Okay, so that is your ds in terms of t. So now we can convert. So in this case, you have to replace everything in terms of t. So your x, so this is your x, and this is your y. Okay, so 1 plus x is 1 minus t, and then your y squared is 2 minus 2t square, and your ds is square root 5 dt, t 0 to 1. So you have to expand that first. So 1 minus t 2 minus 2t, and don't forget should be there is a square. So 1 minus t, we have 4 plus 4t squared minus 8t. Okay, and you have 4 plus 4t squared minus 8t minus 4t minus 4t cubed plus 8t squared. So hopefully we can simplify. 4 plus 12t squared minus 12t minus 4t cubed. Okay, so 1 plus. So we will get 1 plus, we will get 5. 5 plus 12t squared minus 12t minus 4t cubed. And I can take out the square root 5 dt. Okay, and we integrate, and you will get 2 square root 5. The answer is the same. Okay, the answer is the same. Okay, so you look at the notes here. We have the same integral. So look at the question. So we have the same integrand, but the different c. Okay, different curve. Even though we have a different curve, but if you look at the result for the one and the second one, they are the same. Okay, so just look at the notes. What is the question? What is the thing that you have to think about? So the value of the line integral for the example 1 is the same. Okay, which means that it does not depend on the orientation of C. But why? Okay, but why? Okay, so okay, I think for that I will explain you when we comes to it. Okay, there is a property about the path independent when we go to the next section. So as for now, we just compute that. Okay, so we just ignore this. I will back to this notes after we comes to that particular topic, which is path independent. Okay, okay, now we look at the next example. We have to evaluate the line integral for the y with respect to the arc length, where the c is the curve. Okay, this is example 2.